Hello, good morning everyone. Here I'm recording a lecture for the Fridays. It's a makeup of Fridays. Now it's Sunday. Some kind of healthy problem. I cannot go to school actually in the following weeks, not just that Friday. And so all the rest courses, rest lectures, and we're working this way. We record some. I record the video and upload to the YouTube. Then you can watch the lecture in the YouTube. And we have this is for Fridays, and then next that's tomorrow, Monday, and Wednesday we have 2 more lectures. Then it's Thanksgiving holiday. After Thanksgiving we have another 3 lectures. I will use, let me see, 1 for review, and the other 2, or maybe let me see the material. I will see. So the thing is, I will finish the material I will give you, and then give a review, and then the rest of the classes, no lecture. So I will not record the video, but I will set up a Zoom meeting. Then we can work as it's a review and discussion. If you have any question, we can discuss online, in the Zoom meeting. All right, and then the final exam. So final exam will be same with those midterm stuffs. All right, okay. Let's go to today's topic. We are working on a digital control. We want change analog system to be a digital system, and we just studied the method in that 2 method, right? Okay, in the method this is a matched pole 0 method, and modified matched pole and 0 method. We have the corresponding, right? We have S plus A according to Z minus E to the negative AT, right? So we have this correspondent. And this one, we can also say in pole or 0. In numerator is 0, in denominator give us a pole. So I just use P for that. P, suppose this is a pole or 0. Then this one according to pole, this pole should be negative A, right? Should be negative A, so this is just this one. So this pole will be E to the PT. Okay. This pole in 0 in S domain. And this is also a pole or 0 in the Z domain. Right, this is the Z transform. So now we have a relation between S domain and the Z domain. S domain and the Z domain. And in time domain, this is in time domain. This P according to E to the P times T, right? Every pole you can have a term like this in the solution. And similar here, we also have E to the PT. Now it's times N. You have this. In time domain we have these 2. This one, this is a function of T. So when P is given, this function is a it's a determinant, a total determinant. You know T, then you know how it's the value of this function. It's only depending on T. But this one is different. This one, it is, of course, it is also a function of time T, of time N. Now it's a discrete time, as well as T. This is a function not just depending on N. It's also depending on T. You use different sample step. This is sample step. You take sample, right? Different sample step. This will be different. This will be different. Even you have same p, but this might be different. For real number case, it's fine. It is not so strange. But when this is a complex number, you will have sine and cosine term, and you use different step to take sample. Things will be different. You can imagine like a sine, right? You take sample here. It's a 1, -1, 1, -1. If you take sample here, you get 0, 0, 0, 0, right? So for different t, the result signal maybe looks totally different. Yeah. So this is the case. It will happen in the digital case because the whole process is depending on the t. And for our purpose, usually we choose t smaller than or equal to the bandwidth over 20, like this. You can just use this one. Just use this one. The bandwidth, the bandwidth of the system, right? When we do this, we have a system. We want to change the system to be digital. So that system, you give the both plot, you can find the bandwidth. Remember? Yeah, the bandwidth. Right. This is like a g of j omega. You take this one, absolute value in the both plot. Here's the bandwidth, right? Bandwidth. Here's a this is a 70%, right? 70% like this. Yeah, and you use t smaller than this, right? Okay. This is one thing, the relation from the happening in the time domain. So this corresponding in after the transform, they are in the from S domain to Z domain, and before the transform, in time domain it's a continuous time and discrete time t and n, and the relation looks like this. Okay. Now we want to see this p. Right, p, and this is e to the pt. We want to see the relation between them. Suppose p equal to some beta plus j omega. Right, this complex number. And first of all, we can think like suppose beta is fixed. Beta is fixed. Then in the S domain, it will be some straight line, right? Here's a beta. Then the omega, S domain. When omega change, you have a straight line. And this side, in Z domain, what will happen? We just have this, right? We have this one. Oh no, I didn't write here. I'm writing here. Now, P e to the pt equal to e to the beta plus j omega times t. So it is e to the beta t times e to the j omega t. So you see, this is a kind of if we take the absolute value, this will be 1. This is cosine plus sine terms. Absolute value will be cosine squared plus sine squared. Right? EPT equal to absolute value of EPT equal to this is beta t times this is absolute value is a cosine omega t plus j sine omega t. And this one is 1. Right? Cosine squared plus sine squared takes square root, you get 1. So this absolute value of these, it is just this one. Just this one. Now beta is fixed. So this is fixed number. This is fixed number. Fixed number. fixed value, right? A fixed value. And this value gives the absolute value of this e to the pt. So you can see, suppose here is just that e to the beta t, then you will have this curve, right? E to the beta t is here. Then here's omega equal to 0. And here's omega, the angle is omega t. So this is omega equal to 90 degree, right? 90 degree is pi over 2. And over t, so it's pi over 2t, right? Pi over 2t. So omega t is pi over 2. And this point is omega is just pi over t, right? Omega t is pi at this point. And then you turn around, right? Turn around. So here should be 0, then 2 pi over t, actually 2k pi over t. All the 2k pi over t is this point. And this point is okay, it's a 2k plus 1 t pi, like this. Right? So turn around, you turn around infinite times. Every 360 degrees, it will go back to the this point. So it looks like this. So when beta is fixed, you have a circle. In the S domain, it is straight line, up and down straight line, and in the Z domain, it's a circle. Circle. Okay. Circle go across e to the beta t point. So depending on the value of beta, also depending on the t. For large t, you have large circle. For small t, you have small circle. All right. Then in the special case, now we consider 3. So suppose this is 0. And if we compare 3 curves, here's a beta equal to 0. Beta equal to 0. This is just j omega, right? J omega. And this is beta larger than 0. This is beta smaller than 0. And then in the Z domain, beta is 0. If beta is 0, this is 0. E to the 0. E to the 0 so it's 1. Right? So we have 3 points actually. This is 1. And this is e to the, okay, I have to say this both are beta. Okay, I just like this. Just put 1 here. Then we have 3 circle, 1, 2, 3. 3 circle. This one is beta positive. This is beta equal to 0. This is beta smaller than 0. Yeah, I'm writing this way. Yeah, this way. And here, this part according to omega equal to 2 pi times 2 pi over t times k. Right? This is this one. 2 pi over t times k. And this part according to omega equal to still like this one. K will 2k plus 1. Can I write it using term of k? Okay, it's pi over t plus 2 pi over t times k. Right? This is fixed. And this one depending on k. Right? This part you have coefficient k. So along this line, it's like omega equal to this. No matter what is beta. If beta is 0, it will be this point. If beta is something smaller than 0, it's here. Positive is here. Alright. Okay. Then we know about something about the stability. You know? So like this. P according to e to the pt. So it's like here. This side is stable pose. This side is unstable pose. And in the middle is marginal stable, right? Marginal stable or unstable. And then in the Z domain, now, okay, similar, right? this line now is this circle, unit circle, and inside is for beta smaller than 0. So inside is this side, right? So here is stable pose, and outside is unstable pose. Yeah, so this is a similar but different. So for discrete time system, when you have the transfer function, you find all the poles. If all the poles located inside the unit circle, then you know the system is stable. So this is the similar result with the continuous time system. We have all the poles in the left half plane. It is stable. Okay. This is the left half plane. Okay, and if the poles in the Z domain is outside the unit circle, then it is unstable. Z domain, this is S domain. So this is for the stability. Okay, now we look at them in another way. Right here, I say beta is fixed. Then, let me see. Yeah. Then we can consider omega is fixed. What will happen? Here, do we have more things relative? Yeah, it's not important, but it's relative. You know, what is pi over t? Pi over t is the Nyquist sample rate. Pi over t is the Nyquist sample rate. But we take sample. We not just use a Nyquist sample rate, because that one is so close to be the lost information. So if you take sample with a rate higher than the Nyquist rate, you can keep all the information. But if lower than the Nyquist rate, you take less samples, you are lost some information. So Nyquist rate usually is a bound of the is a boundary of good sampling, but that is too close to the bad samplings. So usually we use this one. This is smaller than the Nyquist sample rate. Yeah. Okay. Now suppose for p equal to beta plus j omega. Suppose omega is fixed. Now what is the beta? What is when beta is changing, what will happen? So they say we will have things like this, right? Here's a beta plus j omega. When omega is changing, omega is fixed. This is fixed omega j, and the beta is moving along this line, right? Then this side it is what? We have this is a p, and this is a e to the pt, or equal to e to the beta times e to the j omega, and the t times, right? We have this. Now omega is fixed. This one is fixed. This one is changing. So actually this is what? Omega t. This is omega t, right? You have an angle. J omega t give you an angle, and this is give a different value. This value is from 0 to positive infinite, right? If beta is negative infinite, it is 0. Beta is positive infinite, it's positive infinite. So it's from 0 to positive infinite. Okay, 0 to positive infinite. So it is this one. It's like this. Because depending t. If t is large, this line maybe go to here, or even go to here, right? And it is also periodically. When t large enough, it will go back, right? Yeah. And similar, if omega is large enough, it will also go back. Yeah. So depending on both omega and the t. So here, and if you have the middle one, so here, okay, we still have 3 cases. Actually 2 cases, equal to 0 and not equal to 0. So I give this one. It's j omega. Beta plus j omega if omega is 0. It is just this line. Right? Just this line. Omega equal to 0. Here's 0. Right? Here's 0. Then this line, this is 0, so this is 1. So it is e to the beta t. E to the beta t. E to the beta t is this line. Right? It is this line. Okay. And we have another one. Here. Beta plus j omega if omega over t equal to pi. Negative pi. Here's a negative pi. And this side, this is a beta plus j omega if omega over t equal to positive pi. This is negative pi, this is positive pi. I give some, like I put some dot around this line. What are these two lines? You plug in, this will be pi, right? Omega over t is pi, so omega times t. Put omega over pi t here. Yeah, like here. Yeah. If omega is pi over t or negative pi over t, then omega t is pi or negative pi. So this is 180 degree. 180 degree times this. So we get this one. This is so we have two lines. If the line is here, the real axis, in S domain is the real axis. Then in the Z domain, it is the real axis in the positive side. If in the S domain, the straight line go across pi over t, or sometimes of pi over t, like -1 of pi over t, -2 of pi over t, or -2 is 2 is where we go back. So every 2k plus 1 times, okay, this one, 2k plus 1 pi over t. This one, all of these, the k run from 0, positive -1, positive -2, and so on. Right? If 0, it is just this one. If it is -1, this is -2 plus 1. -2 plus 1. This is -1. So it's a negative pi over t. Right? This one according to k equal to -1. Right? And all these kind of numbers, 2k plus 1 times k pi over t. You have some straight lines. The every straight line, they will go to it. Yeah. So this kind of straight line will go to it. And this one, here, this one is omega equal to 0 or omega equal to 2k times pi over t. Then you go to this line. So you can see in the S domain, you have a sequence of line looks like this. Then they go to Z domain, they are just the two lines, just one line. Some in the left side of the line, and some in the right side. Some in the right side of the line, some in the left side of the line. All right. So this is the case when omega is fixed, but beta is changing. Beta is changing. All right. Okay. Next we can see. Okay, this one. The last one, we go to the pole and zero we did in the purple type system, right? We suppose the pole is a complex case. It's negative zeta omega n plus j times omega n times 1 minus zeta squared. This is the root of s squared plus 2 zeta omega n s plus omega n squared. right? So P looks like this. Then what will happen? Same thing, we fix the one of the value and let another value change, and we can see what will happen. So yeah, we can use computer to do this. Yeah. So first case, suppose like omega n is fixed. What will happen? I go to I have my lab here. Okay. Alright. So we have P equal to zeta and omega. So we need two things. One thing is zeta. I use zeta. Zeta is a value. I give any value. This one is changing. So I use zeta from 0 to with a step to 1. Right? Zeta should be the cosine of theta. Cosine theta. We just use its value from the positive side. This is 0 to 1. Okay, this is zeta. And omega n, we want to fix it. I give any one, like omega n. Omega n, what depending on, okay, it's omega n is the distance from the pole to the original point. So this one is somehow it is absolute value of that pole, and we know it is similar with that. We want it's pi over some times of pi over t. Okay, we just consider it's from pi over t. Okay, it's like this. No, anyway, I just try omega n. Omega n t, I totally time them together. Omega n times t equal to I gave the point connected equal to 0. 0 is nothing. So I from point 1 with point 1 to t. No, I'm sorry. And you fix this, right? I fix like this is just 0.4, for example. Yeah, give a 0.4. But somehow large. Usually we use 7.7. Okay, this is omega. Then P were equal to negative zeta plus j times square root of 1 minus zeta square okay, then the whole thing times omega. Okay, this is P. This is P. Let me see. Matrix. Have negative zeta. Zeta is a sequence of value. And plus j times square root of t. Okay, this one, square. I think this time it works, eh? Give 2 zeros. And times omega n. Omega n t. Actually, it's omega n t. Omega n t. Just omega n. Yeah, we'll see. Do I just omega n? Does that work? If this is omega n, okay, this is a p. Omega n, just omega n. No omega n. So omega n is 0.7. Times omega n. Okay, I have p. If I plot real of p and image of P. What it is? Yeah, this is, I just double check what it is. Okay, this is a omega n is changing, right? Omega n is changing. Omega n is fixed. Omega n is the distance from that pole to original point, so that will be a circle, right? It's a current circle. Yeah, it's a circle. Okay. Yeah, this is zeta from 0 to 1. Okay, and now let z will equal to the exponential power of P times T. Okay, I need a T. Whatever T equal to like a point 0.2, for example. Every second I choose 5 samples like this. Then I get a Z. exp undefined function over exp. Oh, I will type this one, exp zeta equals p times t. Okay. All right. Now I have z, and we can plot z, real z, and imaginary z. Sorry, wrong one. This one still looks like a circle, but not exactly a circle. Okay, this is just one curve. See nothing. We can give more circles. Now I fix the p, right? I fix the p, then I times t. I fix the p and times t. Okay. Sorry, I'm something confused. I have p. I have p for fixed omega n. Omega n is 0.7, and zeta from 0 to 1. Then I get that curve. If I give them more, what happens? Zeta. Yeah, if I give one more. Here I get it. Still okay. I give a 5. Put it in a 5. That'll be fine. I need a zeta. Yeah, I put it in 5. Yeah, that will be good. Put in a 5. Any 5. I start from zeta equal to these. I don't want these. And I want these. Omega n. Give omega n. So this is for fixed omega n, and then I have a p, and then I plot. Oh, I give a t firstly. This one, I give a t, and then z equal to. Usually too much. Yeah. I calculate TP, then I calculate what is a P. This is in S domain. And then I choose a T. I want Z equal to exponential power of T. And then plot what happened in the Z domain. right? So this is I put this is a figure 1, and this is figure 2. So now we can see what happened in 2 domains, right? Figure 1 is for the S domain, and the figure 2 is Z domain. Okay, now we can give more values of omega n and zeta. So here I still first one I consider this is fixed, so zeta I give more. I put t in the front. T equal to 0.2. Okay. And zeta here I use 0. If like I use 0 to 10, what will happen? Oh, I see, this should be cosine. Not so it's like a -1. -1 to this. What will happen? See? Oh, I need to give it a location. I give a location. I put it in the desktop. And 451. 451. Okay, so here I just I give this is a SZ corresponding, right? SZ, just SZ. Okay, SZ. For simple, just save it SZ. And then let's run it. Oh, I need to change my lab. Okay. I have figure 1 and figure 2. We can compare these two. What's the difference? Okay, I can give several omegas, right? I can give several omegas. For omega n equal to, now I choose 0.1. We step 0.1, start from 0.1, we step 0.1 until 1. Okay. Omega could be any, right? I can give some large. I give 3, like x3. For all of these omega n, we do all of these and n. Figure 1, I need a holder none, so I put them here. Figure 1, hold on. Figure 2, hold on. Okay, and before this, I clear or close or clear or alright. Say and the run is F5. Okay, go. Yeah, you see, they are not exactly same. Figure 1 is an S domain, so they are regularly all circles with same center. And now in the Z domain, still looks like circles, but somehow shifted, right? Somehow shifted. So shifted to the more a little bit to the right side, right? So it looks like this. Yeah. Okay, they are the curves for fixed omega. Every curve you have fixed omega. Every curve you have fixed omega. and zeta run from -1 to +1, -1 to +1. And here I have a t is a fixed t. T is fixed is 0.2. If I change this, like for example, I change this to be 5, what will happen? Oh, this one looks more interesting. You see, here are still curves, but this one it looks somehow here not just the shift, also some twisted. Okay, I can change t is 0.5 is fine, but I can give different omega n, more omega n's. Omega n now is to 3. If I give this to 10, maybe it looks more better. To 10, and the step, okay, just step is higher. Step is 1. Okay, just step is 1. Oh, it looks like this. Looks like this. You know, for large omega, it go to like this way. Okay, this is the case for omega fixed. Every curve is a fixed omega, and the zeta is changing. Now we can consider the other side. Right? If now is a zeta is fixed. For fixed zeta, omega is changing. Now I can use similar things like this. Okay, I can copy these. I can give another loop. Okay, now is zeta is fixed, so here's omega n. Oh, sorry, I didn't finish. I didn't times t. I forgot. Sorry. Okay. Here's a t, right? So p is this one, and then the z will be times t. Oh, I times t. Yeah, no problem. Yeah. Then I just copy these. I change these. Here t, this one looks somewhat large. I still go back to 3, maybe better. And here's zeta. This is the first part. Zeta and omega is a point. Use 1, go to 10. I use not 1. I use a point 3, go to 10. Right. Point 1 is too less. Point 1 is too large. Okay, this is for different omega. Every omega fixed, zeta will run from -1 to +1. Now omega change. For every fixed zeta, omega will change. Omega n will change. Omega n, I change omega n from, okay, also 0.1 with step 0.1. That omega to 10, we can also go to 10. And here's also omega n 0.01. Yeah. So this gives us a continuous curve for fixed zeta, but omega n is changing. And hold on. I still hold on these two. I don't need them anymore because I already have it. Right. Now this is zeta. Zeta from 0 to from -1 to +1. -1 to +1 with 0.1 as step, for example, to +1. Yeah, I'm sorry. You know, I eat some pills for the pain relief, and that make me sleepy. I'm sorry, but I can finish this. This zeta is okay. This will be same. Now I still have these two, right? I still have these two. Things should be fine. Just try to run it. Oh, this looks good. It's wrong. Okay, so this is a z domain, right? And this is a time domain. Time domain. Okay, this is the circle are the curves with fixed omega, and the straight line start from original point to somewhere. They are the curves with fixed zeta. Now you see they go to here. They are the fixed zeta. Yeah, we can maybe we can try to see inside part, this part. For this part, then omega is some smaller omega. We don't need to go to 10. We can omega n round to like 5. Omega n go to 5, and here any omega n have 2 omega n, right? P omega n, yeah, go to 5. To 5. Wrong again. Say debug. Wrong. Yeah. Okay. You see, the curve looks like this. Yeah, curves look like this. The zeta from -1 to +1, and after time t from here to here, and omega from 0 to this point. Yeah, we can give a little bit more omega to see what happened here. Okay, omega n. Now this. Omega n to 5. I gave 10 is too much, right? I gave, this is A. Omega n go to A. See, wrong. Oh, it's just a little bit here. It looks not so clear. Actually, in the textbook you can find a figure of this one, and can I make it large? Yeah. Okay, so things look like this. Yeah, you can also find this in the textbook. Textbook gave the figure. They select the interval of zeta and omega just fit, so you can see the figure looks more better than this one. Actually, I believe they give just this part, and this curve will go to omega. They have more omega, so this line, this is a fixed zeta with omega. The omega large enough, it will go to the other side. It goes down to here. It goes down to here. Yeah, we can give more omega. Which one is a fixed zeta with omega changing? This is fixed zeta, and omega changing is here. Omega changing here. Okay, I just give 18. Maybe I give too less. Give 18. What happened? Oh, it's too much. I'm sorry. Okay, just go back. Yeah, just go back. That one will be fine. That figure will be fine. I do all of these. I just want find the figure looks better. Yeah. Okay. So in a figure like this, so you can see if you have you want the continuous system has some kind of pole, and the how to choose the pole in the z domain. You can use this figure. Like along this line should be this line should be the zeta equal to -1. Then some from -1 until 1, right? -1 to 1. So this should be -1, and this curve should be +1, or maybe this is -1, this is +1. Then you can choose from, like you know what is a zeta, you can know it will belong to which line. Also, if you know the omega n, the omega n run from 0 to here until 0 to 1 until 8, right? This one 8. So for large omega n, you pick from large line, right? Then you can pick the pole and the 0 in the z domain just based on this figure. So for some case, for some application, this figure is used for. Not really. This is a kind of early time. People when people do design, they use this kind of figure, similar like the Bode plot, Nyquist plot. They plot the figure, and when they try to design, they base on the figure to measure on the figure to do the design. Now we can directly calculate. But anyway, you should know this figure, this kind of figure. You can find it from the textbook. It looks better than me. Okay. All right, that's all for today. Sorry, a little bit longer. I'm got sleepy. I eat the pill. That one makes me sleepy. Okay. That's all for today. See you next time. Actually, next video. All right. So this afternoon I can record another one. This is for Fridays, and this afternoon I will record the one for the for tomorrow, the Monday morning's class. Okay. All right. Bye bye.